All right, lesson 10.1 is we have two objectives today. We're going to work on the fundamental counting principle, and we're actually going to work on a concept called distinguishable permutations. So those are our two goals for today. But before we get started, there's a concept that I want you to learn. So take about 10 seconds and go ahead and use a calculator and to calculate these real quick. So the first one's really easy because 3 times 2 times 1, 3 times 2 is 6, 6 times 1 just gives you 6. So when you take the next one, let's go ahead and use our calculator here. We can make this a little smaller. This one, I'm going to use this calculator here. So this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you find out that the answer is 40,320. Okay, so pretty easy. Now there is one notation that you're really going to need to be able to use for this, this particular unit that you're going to see come up frequently. If you start at a number, so in case this one, we're going to start at 3. I can rewrite 3 times 2 times 1 as 3 factorial, okay? And that is read as 3 factorial. So anytime you see the word, a number with an exclamation point, it's like I said, it's going to stand for 3 factorial. And this one, since we're going all the way from 8 all the way down to 1, so 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that one's going to be 8 factorial. And you can actually calculate these using a scientific calculator. So if you have one, the buttons might look like they have an exclamation point. They may look like they have an N with an exclamation point. Any of those would actually work. So if I use this scientific calculator, if you'll look at, now this particular one, all my buttons is under math, and then I'm going to go over here with PRB. Depending on your calculator style, they'll be in different spots. So all you're going to do is you're going to type in 3, and you're going to get your PRB button, which is, in this case, is the 4. So it looks like 3 factorial. Hit enter, and I get my 6. Now, if you're using the website, the scientific calculator, you're simply going to type in 3, and your factorial button is right here. So just put 3 factorial. We only need 1, so let me back up a second here. There we go. And up here you notice it says 3 factorial. So then hit enter, and you get an answer of 6. Okay. If you remember the other one, clear it out, we do 8 factorial. It's a little happy on my button, so let's do 8 factorial. And then I hit enter, I get my 40,320. And you can do this for anyone. If I said find 5 factorial, type in, let's clear this, 5 factorial. Gives me 120. Okay, so that is a nice feature about having those. So that was one thing I wanted to show you real quick before we get in. So so let's go ahead and take a look at the next one. And this one is, we want to make a tree diagram to show the total number of lunches that can be made of 1 soup and 1 sandwich. So in other words, for our soups, we can pick chicken noodle, we can pick potato, or they could pick broccoli. And what I mean by a tree diagram is we're just going to branch off. So if somebody picks chicken noodle soup, they could pick ham or they could pick turkey. If they pick potato soup, the sandwich could be ham or turkey. And their broccoli, they could pick ham or turkey. Okay? And so when we're counting how many times, or when we're trying to determine how many total outcomes, we just want to list out our outcomes. So chicken and ham, chicken noodle soup and ham. We could get chicken and turkey. We could get potato soup and ham. We could get potato soup and turkey. Or we could have broccoli and ham. And we could get broccoli and turkey. Okay? So we quickly find out 2, 3, 4, 5, 6 that we have 6 total outcomes that we could actually get from just having 3 soups and 2 sandwiches. Okay? And an easier way that we might be able to find to do that, besides, now this was a pretty easy one, listing out all the possible outcomes, but you're going to find out really quick that listing out all the possible outcomes isn't always the most economical, the most efficient way to do that. So that's where we look at the fundamental counting principle. And the fundamental counting principle basically is just the number of ways that an event can occur. So if we go back to thinking about our soup and our sandwiches, we have 6 different outcomes that we can get, 6 different events, ways that an event can occur. So we could, for example, the chicken and noodle, we could have potato and turkey. And all you're going to do, the total number of events determines, all you're going to do is you're going to take the number of items in the first event, and you're going to multiply those times the items of the second event. Now, if you had three events or 4 events or 5 events or 6 events, then you would use those for all of those events. So let's go ahead and take a look back at our example. So if we were back at our example where we wanted to pick 1 soup and 1 sandwich, okay, all you do is I usually make little lines. So for example, I'm going to pick a soup and I'm going to pick a sandwich. So think about it. How many options do you have for a soup? And we have 1, 2, and we have 3. So we have 3 options for soup. And for a sandwich, we have either ham or turkey. So we have 2 options. And all you're going to do according to the fundamental counting principle is multiply those. And 3 times 2 will give you 6. So we have 6 total outcomes that we could come up with. Okay? So let's take a look at another example. In this example, suppose you own a small deli and you offer 4 types of meat, ham, turkey, roast beef, and pastrami, and 3 types of bread, white, wheat, and rye. How many choices do customers have for a meat sandwich? Now we're going to assume that they're going to pick 1 meat and 1 bread. Okay? So all we're going to do is we're going to pick a meat and we're going to pick a bread. So if you remember, we have 4 types of meat that they can choose from, and they have 3 types of bread that they can choose from. And all we do with those numbers is we multiply. So they have 12 different total sandwiches that they can make with those combinations. Okay? All right, so the next example, go ahead and try this one on your own real quick. So pause the video. But it says a movie theater sells 3 sizes of popcorn, a small, medium, and large, with 3 choices of toppings. No butter, butter, or extra butter. How many possible ways can a bag of popcorn be purchased? All right, so if we look at this, the first option we have to choose from is the size of the popcorn. So if we're picking, we have 3 choices for size, and then our toppings, we're going to pick a topping. And our topping could be no butter, butter, or we could put extra butter. And so we have 3 choices for that option. And remember, we multiply. Fundamental counting principle says we multiply. And 3 times 3 is 9. So they can have 9 different outcomes. Okay? All right, next one. Let's suppose that you're looking at some options for girls' ice skates. So the colors that you have to choose from are white, beige, pink, yellow, and blue. And we're going to assume that the colors of the skates are all 1 color. The sizes that you have to choose from are 4, 5, 6, 7, and 8. And the extras are tassels, striped laces, or bells. And we're assuming that all the skates are sold with with 1 extra. How many possible arrangements exist? So we're going to pick 1 color. We can only have 1 size. And we're going to pick 1 extra. So just like we did before, we have 3 things that we're going to pick. They have a color that we're going to pick. We're going to pick what size of shoe, and we're going to pick the extra. Okay? So you just have to ask, how many choices do I have for a color? If you count white, beige, pink, yellow, and blue, you find out that we have 5 choices for color. And if you count the sizes, we have 4, 5, 6, 7, and 8. So we have 5 choices for size, and the extras, we have 3. So and then we just multiply those, okay? It's no different than if we have 3 events versus if we have 2 events. We're just going to take the number of times we have for the first event times the ones for the second event times the ones for the third event, okay? And we multiply these, and we find out that we can make 75 different kinds of ice skates, okay? Now, the fundamental counting principle, not only determining how many options you can come up with from popcorn to food to clothing, you can also determine how many license plates can be made, or how many passwords, for example. So let's assume that the state of Indiana this is the pattern for the state of Indiana on their license plates, okay, where the first 3 are numbers or digits and the last 3 are letters. So when we're making this, I always make out and say, okay, the first one's going to be a digit. The second one we want to be a digit. The third one we want to be a digit. The 4th, 5th, and 6th one, as you notice, are letters. Okay? Now, unless I tell you, we're going to assume, just like in this example, that in the first spot we put 9, that we can use that number again. So now this is always the tricky part for all the students that I've taught this to. The number of digits is always the trouble. When you think of digits, you're thinking of a single number that you can put in there. So anything 10 and beyond, because we only want one single digit. Okay? So in other words, the double digits, 10, 11, 12, 13, even the triple digits don't work. Okay? 3 digits are going to make, for example, 100. You would take a 1 and 2 zeros. So the digits, when we're talking about digits, we're talking about 0, 1, 2, 3. We could put a 4, 5, 6, 7, 8, or a 9. We can't put 10 because 10 is a double digit. It takes a 1 and a 0. So when you think about it, how many total choices do I have for the digit spot? Well, 1 through 9 is easy. I got 9. When you add the 0 in, I have 10 choices that I can put in that spot. Okay? Now, assuming I can use the same digit, so if I put a 2 in that spot, we're going to assume that I can use, unless it's been specified, I can put a 2 in the next spot. So how many choices do I have for the next spot? Well, I have 10. And then how many choices do I have for the third spot? Well, I have 10. There's 26 letters in the alphabet, so I have 26, 26, and 26. And I just multiply all of those. And after you multiply those, we get 10, 10, 10, 26 3 times. We find out that we can make 17,576,000 license plates. Okay, with that format. Okay. So let's go ahead and take a look at the next one. And you've always got to be thinking about how many options do I have to choose from. So in this example, it says you're taking a test that has 5 true-false questions. If you answer each of the questions with either true or false and leave none of them blank, how many ways can you answer the whole test? Well, we have question 1. You have question 2. You have question 3, question 4, and you have question 5. So assuming you're either going to answer true or false, think about how many options do I have for question number 1. Well, you have 2 options. You can either answer true or you can answer false. Question number 2, how many options do I have? Well, you either have true or false, so you have 2. And so you find out that these are all 2. So one way that you can quickly find out, because we're going to multiply these, well, 2 times 2 times 2 times 2 is another way of writing 2 to the 5th, or 2 to the 5th gives us 32. Okay. Now, think about if you decided to leave one of those blank, how would that change the question? Well, instead of this being 2, now you have 3 options, because you have a true, you have a false, and now you can have a blank. So that would change your problem. Oops. That would change your problem to all of a sudden, now you have 243 possible outcomes. Okay? Let's take a look at passwords. Passwords are kind of like license plates. Actually, this is codes. Codes and passwords. The combinations are going to be the same. It says a company places a 6-symbol code on each unit of product. The code consists of 4 digits followed by 2 letters. How many different codes can be created if the digits and letters can be repeated? Okay, so that basically means, okay, first of all, we got to figure out our pattern. So our pattern is we're going to have 4 digits, so a digit, a digit, a digit, and a digit. Remember, a digit, there are 10, 0 through 9. And then we're going to have 2 letters, so a letter and a letter. So since they can be repeated, how many total digits do you have for that first spot? Well, I have 10. Okay, and assuming I can use the same digit again, so if I pick 3, I can put a 3 in there again, I have 10 choices. And for the third and fourth spot, because they can be repeated, I have 10 and 10. Okay, the letters again, I have 26 and I have 26. Fundamental counting principle says just multiply those and it'll give me my answer. So 10 times itself 4 times, and then 2 26s give me 6,760,000. Okay, so let's take a look at this. The next part, it says how many different codes can be created and the letters cannot be repeated. Now it says only the letters cannot be repeated. Okay, so we're only doing the letters. So that, in other words, that tells me that the digits, you got to and these are problems that you're going to have to read very, very carefully. Okay, so the pattern is still the same: 4 digits followed by 2 letters. And if I'm doing this, well, the digits can be repeated. So those are all going to be 10 because I have 10 choices in all of them. But the letters, think about it. How many choices do I have for that first spot? And you find out I have 26. Well, if I put one letter in that spot, now how many do I have for the second spot? Well, when I take one away, because I put it in that spot, I only have 25. So you find out that 10 times 10 times 10 times 10 times 26 times 25 only gives me 6,500,000. So by just taking away that one letter, eliminates 260,000 different outcomes that I can have. All right. So let's look at this example. In this example, we have 12 skiers that are competing in the final round of the Olympic freestyle skiing aerial competition. So the first question is, how many different ways can the skiers finish the competition? Well, we're going to have first place, second place, third place, and so on. 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, and 12th. Okay? So, no, you always have to think about how many choices do I have. So in the first spot, we're talking 12 skiers. So nobody has crossed the finish line. How many skiers can cross the finish line first? 12. One of them crosses the finish line. Now how many do we have? We have 11. 2 have crossed. We have 10. Now we've got 9 available. 8, 7, 6, 5, 4, 3, 2, and 1. And remember, fundamental counting principle says if I want to determine how many ways this can happen, I'm just going to multiply. Now remember that when I go from a number and I go all the way down to 1, remember, another way to do that, the fastest way, is to do just 12 factorial. Let's pull up our scientific calculator. So we're just going to do 12 factorial, which gives us 479,001,600 different ways. So we have 479,001,600 different ways that 12 skiers can finish the race. All right, part B says, in how many different ways can 3 of the skiers finish first, second, and third to win the gold, silver, and bronze? Well, if you remember in the Olympics, the ones that really matter are the first 3 places. So the gold, silver, and bronze. So nobody finishes the race. How many choices do we have for the first spot? And we have 12. For second place, we have 11, and then we have 10. So we're not really worried about the 9, 8, 7. So in this case, we're just going to multiply 12 times 11 times 10, which gives me a total of 13,320 different ways that 12 skiers can finish the race. Okay? All right. Part 2 of today's lesson is distinguishable permutations. Now, if we want to know how many distinguishable permutations exist in the words mom. Okay? Now, what I've done here is we've identified one of the M's to be red, one of the M's to be green. So, I can rearrange these. If I can get my board to work here. So if I did one, if I move the M over here, the O, okay, that looks different, right? Well, what happens if I move the green one in front and I move the red one in back and we keep that one? I still spell mom, but now I have a distinguishable permutation because the green M is first. But what happens if we're not distinguishing between the two letters? And I say, I'm just going to write this letter in front, and I'm going to put this one in the back. That one doesn't look any different because I can't distinguish between the two M's. So we want to know how many different ways can you actually write the letters mom. Well, M-O-M is one way. I could do M-M-O, or the last one could be O-M-M. And any other combination that I actually come up with, it's just going to get me back to mom or get me back to one of these. So like these two, if I switch these two, I get the exact same thing. That M comes there, that M is in front. Okay? So this is distinguishable permutations. And here's how you find it. Okay? Now the formula looks a lot uglier than it is. But all you're going to do is you're going to find how many total possibilities I have. So in other words, how many letters are there? And the bottom is, how many repeats do I have? Okay, so let's look at the word mom. Mom has 3 letters. So we're going to do 3 factorial. And on the bottom, I want the repeats. And on the bottom, I have 1, 2, so it's just 2 factorial. So if you remember, if you use your scientific calculator, we could do 3 factorial divided by 2 factorial. And we find out that there are 3 different ways that we can arrange the letters in mom. Okay? All right, so let's look at some that are a little more complicated. So for example, we want to look at the letters in Ohio. So we always start out with how many total letters are there in Ohio? Well, 1, 2, 3, 4. And then we just do the repeats. Well, the O's are the only things that repeat, so it's 2 factorial. So 4 factorial divided by 2 factorial gives me, and we can rearrange those letters, 12 different ways. Well, what happens when we have a lot more letters and a lot more repeats? So first of all, you've always got to count how many total letters there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factorial, because there's 11 letters in Mississippi. And then on the bottom, we want the repeats. Well, the M doesn't repeat. The I repeats 4 times, so we're going to do 4 factorial. The S does 4 times, so 4 factorial. And some of you may have to put a multiply sign in there. And then the P's are 2 factorial. So let's see if I can split the screen here. So we can do 11 factorial. Almost. There we go. So we have 11 factorial divided by, now make sure you put this part in parentheses, 4 factorial times 4 factorial times 2 factorial. Close the parenthesis. And if you look right here, this looks like what it's supposed to look like over there. Okay? So hit equals, and you find out, and it may take it a few seconds to calculate, that we have 34,650 different ways that you can rearrange the letters in Mississippi and come up with something different. Okay? So, just as a quick recap, we talked about 2 things today. First of all, the fundamental counting principle is the number of ways that an event can occur. And all you have to do is take the number of outcomes in the first event times the number of outcomes in the second event. And if there's a third or a fourth event, you're going to do the exact same thing. Multiply those. Distinguishable permutation, you want the total number of letters, factorial, over the repeats. Okay? And remember, you have to do each repeat. Okay? All right, so that concludes lesson 10.1. So go ahead, and I would make sure and do some of the practice problems that's provided in there, and then take a look at the quick check. Okay, good luck.